So yes, I'm Christopher Sherman. I'm going to be talking to you today on behalf of myself and Paul Wright and Dick White about ultra-low power sensors for continuous current monitoring. So, well, brief bit of introduction and motivation, building off of everything that we've been through in the last bunch of slide sets. As we all know, smart grid needs smart sensors, and this particular project, its aim is small, inexpensive, low power wireless sensing. Basically, we're designing a sensor to fit into these types of platforms, like the green node that we were just talking about. So to see where we need to fit into things, I'll brief look through the design space that you have to work in for a current sensor. Let's see, where's our light? On our y-axis, we've got our sensor size, small being better for what we're doing in large sensors, and power consumption. Up at the upper left there, we have our essentially what amounts to, from a power standpoint, essentially free. Doesn't really take any energy to run a Rogowski coil, but good luck fitting that into a small platform. Conversely, we can have the other end of things where we can have a small device like the AMRs or the GMRs that we were talking about, where they don't take up a lot of space, but when you're talking about the power budget of something like a node that needs to sit there and run for extended periods of time, these actually end up using really significant amounts of power, and you just really can't work with that for on a limited power budget. So really what we're aiming for is the little red box down here, and let's take a look into that box and see what lives in that box besides us. And there's actually a decent bit of stuff that's been worked on down in that box, although most of it's still up higher than where we need to be. As Igor was talking about, you start to get these sensor platforms where you're looking at microwatt level power consumption, and a lot of these sensors, when you're talking about way up here, this is going to kill your battery in no time. And even a lot of these in the middle, which are approaching, these are state-of-the-art technologies. These are magnetic sensors using things like tunneling magnetoresistive sensors. Now they're very low power, but they're still not quite there. So we're actually aiming for, and this is actually coming out of the models for the devices, is all the way down here at basically single-digit microwatt level power consumption, which actually, even after what Igor has given for the average power consumption of the green node is still a lot, but it's at least approaching the level that we can actually work with. And if you're happening to wonder about this orange dot up here, that guy and its two friends down here, they kind of, I'd argue that they kind of cheat a little bit on the power numbers because they don't actually take into account the entire system. They're just looking at just the sensor itself, not the other parts that you need to actually measure the sensor. And that guy's actually way too sensitive for what we'd be doing anyway. So with figuring out where we need to live, how are we actually getting all the way down on that curve? Well, essentially, we're dealing with a system. Again, we've got a proximity-based sensor. We're not going around We're not going around a wire. We're not galvanically connecting to the wire. Instead, we're doing a transduction method, starting from we've got our wire that's carrying our AC current that produces a magnetic field. We've got a permanent magnet in that field. The two fields couple. It ends up producing a force on the permanent magnet, and if we mount that on the end of a piezoelectric device, or a device that has a piezoelectric layer in it, that force will then produce a strain, which we can then measure, that produces a charge that we can measure off as a voltage. And in this sense, this makes the core sensor itself self-powered. Now, the reason why I don't have us all the way down at zero on the power scale is realistically, like any other type of sensor technology, there's still a little bit of reference circuitry that needs to happen. Although that can be really low on the power budget, and that's actually where the only power consumption of the system actually comes into play. So with that in mind, and also when we're looking at we're transducing, we're taking small amounts of energy from this. We need to look at is this really just a sensor at this point? And well, at the large scale, and by large I mean relatively speaking, I'm talking like this scale large, still pretty small, but this is a mesoscale piezoelectric device. And these actually, you get quite a lot of charge here. You've got a lot of volume of material, you've got a lot of mass on the end to play with, you get a lot of energy comes out of it, and you don't really care in this case, for the most part, what's actually connected down at that end where we're marking V out. Basically, you can treat it purely as a sensor. When you start to shrink this down to take advantage of our, to make small devices, to take advantage of our MEMS processing techniques, it starts to become a slightly different set of circumstances, though. You've got a lot less material to work with. In the case of our magnet on the end, there's a lot less volume there. There's a whole lot less energy present to play with. Suddenly, you have to start looking at, okay, what am I actually hooking to the end? Hopefully, not our friend the ant, but what am I actually hooking to the end of this device? And you realize it's starting to behave a lot more actually like an energy harvester. And really, when you look at the rest of the system, you realize that, okay, to get anything useful out of this device, we need a reference resistor, which is essentially a load. And we actually need to tune for that just like we would tune any energy harvesting system. And there's actually, and then you start to look at, okay, well, what can we actually do to tune this thing? What can we do to optimize this? What can we do to make this work and for what we're trying to get out of a system like this? And you realize, okay, we can play with magnet sizes, geometries of these things, layer thicknesses. Where do you start? It's actually a huge system to work from. And, well, as it turns out, one of the really good places to start looking on this is what I'm calling aim for the sweet spot. Namely, well, we know that we're looking at, in this case, this is AC current that we're trying to make sense out of. We know that the AC power system, at least in this country, is primarily running off of 60 hertz, 50 if you're in Europe. But and we know that you can pretty much get the information you need out of that by monitoring just the harmonics, 60 hertz, 180, so on. So if we know we're targeting those harmonics, we can actually be smart about how we design the sensor. And if we know that we can't really go too far up in frequency before we start to really lose sensitivity on these things, we can actually design our resonant peak, our natural frequency of the device, such that it will actually straddle a couple of the harmonics. And at that point, we can pick up everything that's below it, in this case, just one of the harmonics. But we can also pick up one frequency beyond it if we're smart about how we design this, and then still have essentially a flat response for the harmonics. So, okay, we have a way of figuring out where we're aiming on the frequency. Well, what about the geometric parameters of this? Well, as it turns out, a really good way of doing this is to actually optimize for dynamic range, which, just in case anyone in the room is not familiar with this, it's just maximum signal over minimum signal. And as it turns out, dynamic range in this case, if you have the rest of your system defined properly in the model where you're doing your optimization, it basically accounts for everything that we need to know, everything that we really care about in designing a sensor like this. It accounts for our raw output. It accounts for things like, okay, what are our maximum outputs that we can expect based off of, say, film stress, or say, linearity limits to the point where the thing starts to behave in ways we're not expecting. This also accounts for things like the minimum signals that we would get from, say, for example, okay, well, we've got a thermal limit, or we've got a limit set by the thermal noise going through the resistor, and we've also got some realistic limits set by the whatever circuitry we're connecting to. So if we can we aim for, like I said, we basically aim for the sweet spot and then follow up to the curve until we get to the point with the maximum dynamic range. So that still leaves one big thing in terms of if we're going to try and optimize this system, namely material selection. What are we actually going to make? What are we actually going to make this particular piezoelectric sensor out of? Well, the two big obvious choices, the old classic one, which is PZT, lead zirconate titanate. Yes, it contains lead, and it actually works very well as a piezoelectric material. And the other one, the newer material, aluminum nitride. Now, if you were just looking at this as a pure sensor, if you actually didn't pay any attention to the rest of the load that was present, you would find, you might think that, okay, well, the aluminum nitride is actually giving a better output. But then when you start to look at the rest of the system that you have to take into account, like you realize that you end up with a system that the PZT actually gives you a better dynamic range. It requires a much smaller reference resistor, which is actually good because 100 megohms is actually kind of hard to instrument properly. Things get kind of sketchy with a lot of circuitry there. And the aluminum nitride device ends up to get to the same places because of the nature of aluminum nitride, the stiffness and the low capacitance of the films. You end up with a device that's 9 times as large. So we're talking in this case, to get to basically the same place, we're talking about a device where the core of the device is almost 4 millimeters long. So yes, we know that PZT is no saint here. It's got lead in it, but for the sake of maximizing our dynamic range and being able to instrument this thing, the project has been proceeding with PZT for now, although we're still considering looking at ALN variants in the future. So, what are we actually producing on this? Well, here's our layer stack. Up the upper right here is actually the core of the device, which is essentially just, here's our piezoelectric cantilever. Here's our magnet on the end. Here's what it would look like as a chip form with 2 of them, 3.4 millimeters on the side, roughly. And then here's our layer stack. Now we're going to be I'm going to take you through some brief stuff on some of the layer stacks, some of the progress we've made on that. But mostly focusing up here in terms of we've got an upper electrode, which is a chrome gold layer. We've got our piezoelectric material, which is our PZT thin film, and we've got a ti-platinum lower electrode below that. All of that sits on a silicon cantilever with our proof mass on the end, which is also our magnetic material. And speaking of that magnet, any of you who have seen these talks before by myself or by Eli Leland when he was giving them will remember the picture on the left there with our little pile of magnetic material, our cannonballs on a diving board, as it were. So this is out. Time has marched on, technology has advanced, and we no longer need to do this to get small magnets. There are now actually commercial companies that are now capable of producing large quantities. In this case, there's about 100 of them there. These are 850 micron on a side rare earth neodymium magnets that are of suitable size to use for our devices. These are both higher energy than what we had here, and it's a lot more consistent, a lot more reliable. It's hard to tell what you have here for what's the volume of this thing, what's the actual output of it versus here's a cube. It's pretty easy to work with. So that's our proof mass on the end. Well, how about our films? Well, the PZT film has actually been coming along pretty nicely. We're building off of some pretty well-established sol gel processing, which, without getting too much into the details of that, it's basically spun on and crystallized. So we're getting good thicknesses. We're getting a good mirror-like finish, which is actually what we want to see in this case. And if we zoom in on this stuff, we see that we've got the layers are actually established well. We've got good epitaxial growth through them. Yes, I'm speeding up because I'm running out of time, we've got a pretty nice piezoelectric film sitting there. The film on top of that is likewise in good shape. This is our upper electrode. This is chrome gold. This is using actually another well-established process, which is lift-off. If you want more details on it, talk to me. Okay. And this is actually, we're getting good definition. We're getting our layer thicknesses right on the money, which for UVAP is about as good as you can possibly ask. And things are good film adhesion, good definition on that. Stepping down to the lower electrode, I'm bringing up one of the classic cars, as it were, of the Nanolab, our old argon mill, which is known as ion mill. The lower electrode is primarily made out of platinum. Platinum is difficult to process in terms of etching. There's not a lot that actually works through it. So what we're doing here is argon milling. This is basically accelerating an argon atom and blasting it into a surface, knocking bits off of it. It's bead blasting with atoms. The process is limited to 4-inch wafers. We're hoping that they're going to bring another tool online in the future that'll get around that, but for now we're working with 4-inch wafers. And that actually brings me to my last slide, which is the one that Paul already brought up, which is our near finished process wafer. This hasn't actually had the underlying silicon etched through yet, but this one has had basically to the step you see here, which is it's had a large amount of the pattern definition. The films are defined. and we just need to start to do the release steps on it. There are still model refinements in progress, or there's still, this is likely to get another mask set before all is said and done, but it's moving in the right direction, and I've been pretty happy with how it's going, and with that, I'll take any questions. In practice, you may need a little bit of tuning, but then again, a lot of these MEMS devices, even in mass production, they do a bit of tuning, like even with like F-bars. They'll use, if I remember correctly, they use a laser ablation system to dial them in. So it's quite possible that there would be some tuning necessary.
Hi, thank you. This is terrific development. I'm curious to know whether you've done any intended radiation, either conducted or radiated testing or concepts around that, or noise susceptibility.
Susceptibility to noise. I mean, are you talking like a electric field noise? You're talking magnetic? Yeah. Well, this actually did come up briefly. Someone else was asking about this earlier. And worst case scenario on a device like this. Well, we're measuring for a magnetic field. We don't actually care what the electric field looks like, so you can always just put shielding around it, and the magnetic field will still get through that, but the electric field will not. There has been, which is actually what the solution that Eli Leland on his portion of the project had ended up doing for his. He just dropped his devices into just a little box that had aluminum around it, and the electric field noise basically went away at that point. He was also dealing with a much higher impedance device, so things were inherently noisier to begin with.
How accurately do these have to be positioned with relative to the power cord in order to work consistently?
Yes, the elephant in the room, as it were, on this. Now, if you just have one of them, that gets to be kind of tricky, and you start to have to look at things like, okay, how are we going to calibrate this, and so on. This is actually something that our group has looked at actually fairly extensively. Actually, this is one of these things where one of my lab mates, I wish he was here today because he's done a huge amount of modeling on this, where one sensor by itself, you need really good calibration. But if you start to look at multiples of them, like in the case of, if you're talking about a single wire, which is mostly what I've been looking at for my portion of it, you can actually do self-calibration with just two sensors. You just need to know where they are relative to each other. And then it just becomes a system of two equations and two unknowns. If you're talking about more sensors, you can still back out what you need to know. More wires, you just need to have enough sensors to do it. So there's the alternative. You can either calibrate for one or you use multiple sensors. Any other questions? Do I see a hand there? Yes, no? Yeah.
Okay, thanks again, Chris.